In this section, we're going to be looking at the hypothesis test for a population mean where the population standard deviation is unknown. So our objectives in this section is to test the hypothesis about a mean using the p-value method, and the second objective is to test the hypothesis about a mean using the TI-83 or 84. So here we're going to test the hypothesis about the mean using the p-value method when we do not know the population standard deviation. So we begin this section with an example. Suppose that a recent medical study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was 2.2 kilograms with a sample standard deviation of 6.1 kilograms. We conclude that the mean weight is greater than 0. If we knew the population standard deviation sigma, we would be able to compute the z-score of the sample mean to be z equals x bar minus mu over the standard error, sigma, divided by the square root of n, and use this test statistic to perform the hypothesis test. In this example, as usually the case, we do not know the population standard deviation. To proceed, we replace sigma with the sample standard deviation, S, and we use the t statistic instead. So here we have t is equal to x bar minus mu divided by s divided by the square root of n. When the null hypothesis is true, the test statistic has a student t distribution with n minus 1 degrees of freedom. So now we're using the t distribution for our sampling distribution for x bar. The assumption for performing a hypothesis test for mu when the population standard deviation sigma is unknown are as follows. We have a simple random sample, and the sample size is large, n greater than 30, or the population is approximately normal, which in some cases we have to discover. Now suppose that a recent study of 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was 2.2 kilograms, with a sample standard deviation of 6.1 kilograms. Can we conclude that the mean weight loss is greater than 0? Since we have a simple random sample and the sample size is large, we may proceed with the test. The issue is whether the mean weight loss, mu, is greater than 0. So the null alternative hypothesis are 1, the null hypothesis is mu is equal to 0 versus H1 where mu is greater than 0. So from our sampling distribution, we see that we are testing from the sampling distribution, the t distribution, where the t value is in relationship to this t distribution. The test statistic t is calculated by x bar minus mu divided by s divided by the square root of n. When we plug the numbers in, 2.2 is x bar, 0 is mu naught, 6.1 is the sample standard deviation divided by the square root of 76. We get a calculation for t to be 3.144. When h naught is true, the test statistic t has a student t distribution with 76 minus 1 degrees of freedom. This is a right-tailed test, so the p-value is the area under the student t-curve to the right of 3.144. It's right here. And using technology, we can find the exact p-value to be 0.0012. Since the p-value is less than 0.05, we reject H0 at alpha equals 5% significant level, and we conclude that the mean weight loss of people who adhere to this diet for 12 months is greater than 0. The p-value of the test statistic t is the probability of assuming H0 is true, of observing a value for the test statistic that disagrees as strongly as more strongly with H0 than the value actually observed. The p-value is an area under the student t-curve with n minus 1 degrees of freedom. The area is in the left tail, the right tail, or in both tails depending upon the type of alternate hypothesis. So each one of these we're determining where mu is and where the value t is in relationship to mu equals 0 under the sampling distribution. Notice that in each one of these cases we're looking at the number of standard deviations x bar is from mu naught. So, we're estimating the p-value from the table. When using the t-table, we cannot find the p-value exactly. Instead, we can only specify that the p-value is between two values, typically. In the last example, there are 75 degrees of freedom. When we consult table A3, we find that the number 75 does not appear in the degrees of freedom column. We therefore use the next smaller number, which is 60. Now look across the row for the two numbers that bracket the observed value 3.144. These are the numbers 2.915 and 3.232. The upper tail probabilities are 0.0025 for 2.915 and 0.001 for 3.232. The p-value must therefore be between 0.001 and 0.0025. We can conclude that the p-value is small enough to reject H0 at the significance level 5%. So suppose we had a different hypothesis. Suppose our alternative hypothesis was H1 is mu not equal to 0. The p-value would be the sum of the areas in the two tails. If using table A3, we can only specify the p-value is between two values. We know from table A3 that the area in one tail is between 0.001 and 0.002. Therefore, the area in both tails is twice 0.001, which equals 0.002, and twice 0.0025, which equals 0.005. So in both cases, we would still reject the null hypothesis at the 5% level. So now we'll look at a second example. Generic drugs are lower cost substitutes for brand name drugs. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. The U.S. Food and Drug Administration is now supervising the testing of a new generic antifungal ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredient to each square centimeter of skin. As a part of the testing, 7 subjects apply the ointment. 6 hours later, the amount of drug that has been absorbed into the skin is measured. The amount in micrograms are the following data set. How strong is the evidence that the mean amount absorbed differs from 3.5 micrograms? We use the significance level 0.01. Well, the solution is, first we check the assumptions. Because the sample is small, the population must be approximately normal. Here, the book uses a dot plot of the data, and typically we may use a box plot or check for skewness in Excel. Well, in this particular case, the dot plot shows that there doesn't seem to be any major skewing, and there doesn't appear to be too many outliers. There's no outliers at all. The null and alternative hypothesis H0 mu equals 3.5 versus the alternative hypothesis mu does not equal 3.5. We compute x bar and s from the sample. The values are x bar is 2.9429 and s in this case, which is the sample standard deviation, is 0.4995. Again, we don't know the population standard deviation. So in this example, the test statistic is t, and in this case, we see that we are going to calculate, we'll put down that t is equal to x bar minus mu naught divided by the sample standard deviation divided by the square root of n. And when we do the calculation, we put in all the numbers into our calculation, and we get a negative 2.921. The number of degrees of freedom is n minus 1, which is 6. So the alternative is a two-tailed, and so the p-value is the sum of the area to the left of the observed value t statistic, 2.951, and the area to the right of 2.951. Using table A3, the two values closest to 2.951 in the row corresponding to 6 degrees of freedom are 2.447 and 3.143. So the area to the right of 2.447 is 0.025, and the area to the right of 3.143 is 0.01. Therefore, the area in the right tail is between 0.01 and 0.025. So the p-value is twice the area in the right tail, so we conclude that the p-value is between 0.02 and 0.05. Well, in this case, the p-value is small enough to give us doubt about the truth of H0. However, because the p-value is greater than 0.01, we do not reject H0 at the 1% level. So in this case, there is not enough evidence to conclude that the mean amount of drug absorbed differs from 3.5 micrograms. The mean may be equal to 3.5 micrograms. Our second objective is to test the hypothesis about a mean using a p-value method and using our technology, the TI-84. So, in a previous example, we supposed that a recent medical study of 76 subjects were placed on a low-fat diet. after 12 months, their sample mean weight loss was, X bar was 2.2 kilograms with a sample standard deviation of 6.1 kilograms. Can we conclude that the mean weight loss is greater than 0? Since we have a simple random sample, the sample size is large, we may proceed with the test. The issue is whether the mean weight loss is greater than 0. So, the null alternative hypotheses are H naught is mu equal to 0, H1 is mu greater than 0. Again, the test statistic is t, and when we put in the information from our example, we find that we get a t value at 3.144 when H naught is true. The test statistic t has a student t distribution with 56 degrees of freedom. And again, under our technology, we can find the p-value that is to the right of the value t equals 3.144, and we find that p-value to be 0.0012. Again, with a significant level 0.05, we can reject H naught, and we can conclude that the mean weight loss of people who adhere to this diet for 12 months is greater than 0. Well, in the previous problem, we're going to use the TI-83 or 84. To do that, we will calculate the t-test and perform a hypothesis when the population standard deviation is unknown. This command is accessed by pressing the Stats and Highlighting Tests menu. When we do that, we get this screen, and you can notice that option 2 is our t-test. So if in fact we have summary statistics like in the previous example, we will select the stats option. Otherwise, if we are given data, we will select the data option. So in our previous study of 76 subjects that were placed on the low-fat diet, we found that X bar was 2.2 kilograms, S was 6.1 kilograms, and the question was, can we conclude that the mean weight loss is greater than 0? So now we can set up our hypothesis test right away. H naught, right, is mu is equal to 0. H1 is mu greater than 0. And so we press the stats key, highlight tests, and we select the t-test. Now we select stats because we have the information. We select the stats key. We enter 0 for mu naught. We enter 2.2 for X bar. We enter 6.1 for SX, and N is 76, and we come over here to our alternative hypothesis of greater than mu naught. We hit calculate, and sure enough, here is our result screen. It tells us what the t-value is, and it gives us a p-value of 0.00119. So in this particular case, the p-value is 0.0012, and we reject H naught at the 5% significance level. And we conclude that the mean weight of loss of people who adhere to this diet for 12 months is greater than 0. So now we look at the generic drugs the low-cost substitute for a brand name. And this is also a previous example, but we're going to use the TI-83 or 84 for this particular example. We were given the brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredient to each square meter of skin. As a part of the testing, 7 subjects applied the ointment. 6 hours later, the amount of drug that had been absorbed into the skin is measured, and the amount in micrograms are the following data pieces. So here they are, and the question is how strong is the evidence that the mean amount absorbed differs from 3.5 micrograms? Use alpha at 0.01 level of significance. So again, we can set up the hypothesis immediately. What we will be looking at is mu is equal to 3.5 versus H1, where mu is not equal to 3.5. And so we check the assumptions, and we're going to check the normality issues. And on the TI-83 and 84, typically we can't do a dot plot, but we would be able to use a box plot. So I suggest a box plot if we're using our technology, and if we see any outliers, then we know that we do not have a normal distribution. Also, we will then go to our next slide. And now we enter the data into L1 after we hit the stats key. Once we hit the stats key again after we've entered the data, we move over to the test option and we select the t-test. Now, since we have data in our calculator, we're going to select the data option, and we enter in our hypothesis, null hypothesis of 3.5. Our list is in L1. Our frequency we leave alone, and our alternative hypothesis is not equal to. Then we hit calculate, and the p-value, it turns out to be, so here's the screen, our t-value is negative 2.95, and our p-value is 0.02558, right? So if we're trying to see how well this fits with a p-value of less than 1%, in this case we cannot reject H0 at the 1% significance level because our p-value is 0.0256. So in this case, there's not enough evidence to conclude that the mean amount of drug absorbed differs from 3.5 micrograms. The mean may be equal to 3.5 micrograms. So in this section, the assumptions for the hypothesis test for mu when sigma is unknown. So we have to make sure that the assumptions for the hypothesis test are correct, and then we should know how to perform the hypothesis test for mu when sigma is unknown using the p-value method and calculating the t-statistic. And finally, we know how to estimate a p-value from a table for a one-tailed or two-tailed test. And we know how to use our calculator. So this concludes chapter 9-3 on the t-test, we will now go to talking about testing for a proportion from the population, a qualitative variable.